Welcome to this session of Shadow the Scientist. My name is Jamaica Marshall, and I'm very pleased to serve as the Shadow the Scientist Coordinator. And I'll just say that I am live here at the Maunakea Visitor Information Station, just below the 10,000 foot level tonight. And so if you hear some people in the background, that is our amazing crowd that is here for this session. All right, yeah, make some noise. Okay, so without further ado, let's move on because we're started a little bit late. So thank you all for being here, those of you in our live audience and those of you in our virtual audience. Now, Shadow the Scientist is an initiative offered by a team at the University of California at Santa Cruz. If I can find my cursor, we can introduce our amazing observing team. So tonight we have the privilege of shadowing members of the C3VO team, and maybe they can get into explaining what that stands for. Now, that includes Dr. Brian Lemaux of Gemini Observatory North, NOIRLab, Dr. Shen of Texas A&M University, and Dr. Roy Gao of the University of Hawaii's Institute for Astronomy, Dr. Ben Forrest of the University of California, Davis, Dr. Ekta Shah, also of the University of California, Davis. And if you, I know our live audience just heard from Ekta that she's not doing well and had to sign off, but we are so thankful for her contributions to all of our C3VO sessions, and look forward to having a session with her this Sunday. And we also have with us Mr. Finn Giddings, as well as Joel Diamond. So we are very, very thankful to have the C3VO team here with us. And I'm going to pause just for a moment because I believe Brian has joined us. So let me stop my share here and make him a co-host. Let's go back and make this a larger screen again. Yes, we have the Subaru Hilo base facility. So let's welcome them. Yes, let's make them a co-host. All right, and let's see who we have at the Subaru Hilo base facility tonight. And there we have Aloha, Brian. All right, so I'm going to go back to my introduction or picking up, and now we have everyone of the observing team with us tonight, which I am super, super thrilled about. Let's find where I was. All right, so yes, we will be shadowing these amazing members of the, yes, I'll make you co-host on the other Subaru Hilo host in just a moment.
Okay, no problem. Thanks, Jamaica.
Thanks, Brian. Okay, so now the C3VO team will be using the multi-object infrared camera and spectrograph on the Subaru telescope this evening. So now they're going to be targeting several suspected large structures of matter that were under formation when the universe was about 20% of its current age. The goal? They're searching for missing galaxies in these structures. They're going to also be estimating the number of stars that the galaxies form and trying to understand how galaxies are transformed as they assemble into these massive structures in the early universe. Now, those of you who are here with me live at the Visitor Information Station, we have this beautiful background here where we can see all of the telescopes that are on Maunakea. Subaru is here right on the left. Now, the Subaru telescope is an 8.2 meter optical infrared telescope. And as you know, it's near the summit of Maunakea and is operated by the National Astronomical Observatory of Japan. Now, tonight, the team will be, again, using this multi-object infrared camera and spectrograph in their research. So without further ado, let me stop my share and let's head over to the team to get us started. Let's begin with Roy. Roy, welcome.
Aloha, thank you, Jamika, and Shadow for hosting. My name is Roy Gal. I'm a faculty member at the University of Hawaii's Institute for Astronomy in Honolulu, Manoa. I'm actually at home. You may hear my kids and stuff around in the background. Um, that's one of the nice things about modern technologies we can observe from anywhere. So I'll be doing some slides about telescopes and optics and our science a little bit later on after the introductions. And I'm pretty sure Brian, who we'll see later, is getting very busy setting up and starting the observing for the night. So later on, he and Finn will share their screens and we can actually see them observing.
Excellent. If you'd like to, Joel, introduce yourself, then we can have Finn do an introduction, and then maybe we can go over to Brian at Subaru.
Hi, I'm Joel. I'm an undergraduate student at the College of Charleston. I'm in my senior year, and I recently joined the C3VO research group, thanks to Roy Gal. Thank you very much for that, by the way. I'm currently, this is my second observing run with Subaru, and I'm working on some narrowband research with a couple of the members.
Wonderful, Joel. Welcome. It's fantastic to have you in our shadow session. Finn.
Hello, everyone. My name is Finn Giddings. I'm a third-year graduate student at the Institute for Astronomy at the University of Hawaii, Manoa. I'm currently at my office right now doing some observing, but I've been working with the C3VO for a couple years now, and I look at galaxies that are interacting and merging together in in structures that are really far away in the universe, kind of distant structures. Yeah.
Sorry. Thank you, Finn. And now we have Brian.
Okay, aloha, Jamika. Hi, Finn. Hi, Joel. Hi, Roy. Roy, thank you for joining us. My name is Brian Lemaux. I'm a staff scientist at the Gemini Observatory. So I don't know how many people are there or how many people went up for sunset, but Gemini is that the biggest telescope on the East Ridge. It's the one that opens up and has the vent gates and looks kind of weird but pretty. And I'm observing on the Subaru telescope. So we share time. Each telescope has different strengths and weaknesses. And so I'm observing in Hilo tonight. So I'm at the base facility for Subaru. It's on the University of Hawaii Hilo campus. It's actually right next door to the Gemini base facility, and I'm helping the Gemini observers tonight as well. So I'm kind of running in between the two different telescopes. Yeah, so I help with Gemini operations. I observe at night. I help plan all the observations. I help maintain some of the instruments there. But I also do a lot of my own research with Roy and Finn and Joel and others. And this is one of the nights that I get to do research for the most part. And that's super exciting. And as I think Roy and Finn and Joel mentioned, I'm part of this C3VO collaboration, which is charting cluster construction with Woods and NOIRLab. It's just acronyms nested inside of acronyms inside of acronyms. And it's just a fancy way of saying we're looking for galaxies about 2 billion years after the Big Bang, and we're looking for very big structures of galaxies. And as I think Jamika mentioned in her opening, the particular objects that we're looking at tonight, we know there's a big structure of matter somewhere in the universe, and this actually comes from a different telescope in the southern hemisphere called Magellan. We're able to see that there's a lot of neutral hydrogen gas, like kind of floating out there in the universe. There should be a large structure, but we don't see a whole lot of galaxies so far. And so Subaru is awesome at seeing a lot of galaxies at once. And so we're trying very hard to see those galaxies. And if we don't see those galaxies, it's super interesting because where did the galaxies go? And if we do see those galaxies, it's also super interesting because those galaxies are probably going to be different than the galaxies that we're used to. So super exciting. huge mystery, and yeah, we hope to figure it out tonight. And as I guess people know from coming down from the summit, the conditions are actually pretty nice tonight. So it's a little bit humid. It's kind of spiky in terms of humidity. But actually the clouds right now, knock on wood, never tempt Maunakea. The clouds right now are not there. So we're happy. We're open, we're happy, we're observing good photons.
All right, yay for photons, fantastic. Okay, so I believe, Roy, you wanted to give us a bit of an introduction before we get started with the science.
Yeah, I thought I'm not sure exactly who the people in the audience are in terms of their experience and knowledge. So I thought I'd do a little review of telescopes and their purpose, and then a little bit about Mauna Kea telescopes and astronomy in particular, and then talk a little bit about galaxies, and then we can get into the details of our science. So most people are familiar with sort of like household telescopes, the long skinny one you might buy for $100 in a Walmart or something like that. So the real question I want to ask people is why do we even bother using telescopes? And the answer to that you already probably know from your biology. So what happens to our eyes when it gets dark? The pupils dilate, they get bigger to let more light in. So if we wanted to see super faint things, our eyes could get even bigger, our pupils could get even bigger, and we could see very far away galaxies with our eyes. But our eyes are fixed balls of liquid, so we can't make them super big. So we build bigger and bigger telescopes for two reasons, actually. One is to collect more light to see fainter things. And the bigger we make it, the more light we can collect. Much like the more solar panels you put on your house, the more light from the sun and energy from the sun you can collect. So the amount of light we can collect scales with the area of the telescope. And when we talk about a telescope like Subaru or Gemini being 8 meters, we're talking about the diameter of its circular, usually circular mirror. So the area goes as the diameter squared. So if we make a telescope twice as big in diameter, it has 4 times the light collecting area. That's like going from having 4 solar panels to 16 solar panels. If you, right? So that makes a big difference. But the other thing that people don't appreciate a lot of the time is that the bigger we make the telescope, the more fine detail we can see. So here's an example of the same galaxy pictured with 2 different telescopes. And as you can see, there's a lot more detail you can see in the right-hand picture, and we can learn a lot more. And if we can get rid of the blurring of the Earth's atmosphere, or we can launch a telescope into space, then the detail we can see scales linearly with the size of the telescope. So if I make my telescope twice as big, I can see twice as fine detail. So for those of us who have glasses, that's like going from 2020 to 2040, from 2040 to 2020 vision if I double the size of my telescope. So that's the reason we make telescopes. And most of the telescopes that we use, at least for optical and infrared light, the kind of light we can see with our eyes or that cats can see with their eyes, use mirrors made of glass or glass ceramic composites. So that's a little bit of background on telescopes in general. So we're using these big telescopes because we're looking at far away galaxies, and they're very faint, just like seeing car headlights far away. So I want to talk a little bit about the telescopes on Mauna Kea. So I'm going to switch to another slide deck. So those of you who are on Mauna Kea now, like Jamaica and some other people, are sitting right here on this mountain that's in this picture in the middle of the ocean. This is a picture of Hawaii Island taken from the International Space Station. That's what you see here at the bottom is bits of the space station. I think that might be part of the Canada arm down there. So we're here, or some of you are there. Our telescope is here. And the reason we have telescopes on Mauna Kea, I'll talk about that in a few minutes, but we are on the most isolated island chain on the planet. And it's pretty remarkable given that there's a couple 100,000 people or over 1 million people amongst all the islands of Hawaii. But being on this isolated chain in the middle of the ocean on a tall mountain gives us really great observing conditions. And to put it into context, telescopes in astronomy have been growing over the years. And if we look back about 100, almost 130 years, the biggest telescope was only 40 inches across. And we go back just 100 years, the biggest telescope is 100 inches across. And then in the middle of the last century, we're talking about 200 inches or 5 meters, so actually quite a large telescope for that time. But telescopes the size of Subaru and Keck and Gemini have only been around for the past 30 years or so. Now, the history of on Maunakea, which we all now know as a place where there's lots of telescopes, actually starts with no telescopes on Maunakea, and people even thinking that we couldn't build telescopes at the elevation of Maunakea, which is almost 14,000 feet. But in 1960, tsunami devastated Hilo town. Some people like Brian are at the Subaru Hilo base facility, so he's right in the area a little bit inland of where this picture on the screen was taken. And it doesn't sound like the tsunami should have anything to do with astronomy, but it actually motivated the Chamber of Commerce there at the time to figure out how can we redevelop our businesses. And the executive secretary of the Hawaii Island Chamber of Commerce knew that telescopes went on big mountains. So he said, well, maybe we could get people to come build telescopes here and help our economy. And he invited a number of astronomers who ran observatories to come and check out Maunakea. And the only one who said okay was Gerard Kuiper. And many of you may not recognize that name from the Kuiper Belt, to which Pluto was demoted. But he came from the University of Arizona's Lunar and Planetary Laboratory to check. And the reason other astronomers didn't come is they really didn't think that it would be possible for humans to work and build at this elevation. But he came. At the time, the University of Hawaii had exactly 0 astronomers, and Hawaii hired 1 astronomer who was actually a solar physicist. And between determining that Maunakea was an incredibly good site for astronomy, and Hawaii University starting to get us involved in astronomy, we have developed to where Maunakea is today, with almost a dozen operating telescopes, and as the premier site for astronomy in the Northern Hemisphere and possibly on the entire planet. Just as skipping ahead a couple of decades, the first large telescope was the UH 2.2 meter or 88-inch telescope, which is still operating. It celebrated its 50th anniversary a few years ago. But in the 1990s, a number of large telescopes were developed, including the twin Keck telescopes by UC and Caltech, the Subaru telescope, which we are observing with today, and the Gemini North telescope, where Brian is gainfully employed. And to put these telescopes into context, the first large telescope I mentioned is this 2.2 meter telescope here, the UH 2.2 meter. Then there's a bunch of 3 to 4 meter class telescopes that are still operating on the mountain. And the Gemini and Subaru telescopes you see down there, and the Keck telescopes, which are segmented and pave the way for telescopes like James Webb. And if we ever build a 30-meter telescope in the future, that's what this big hexagon shows in comparison. So these are the telescopes we have up on Maunakea. This small one is, these are the optical infrared telescopes we have on Maunakea. It doesn't show any of the millimeter wave ones. And to put those into context with telescopes around the world, you can see in the blue here, the 2 Kecks, Gemini and Subaru, the planned 30-meter. Europeans are building a similar size telescope in the Southern Hemisphere. And this gray donut was what we would consider insane European idea to build a 100-meter telescope. But you can see there are quite a few large telescopes in the world, but not that many that all the astronomers have to share. I think I'll pass over the site testing, but Maunakea was shown to be a premier astronomical site, and that's why we have all of this here today. All right, so I don't know if Brian has a minute to share about observing. Otherwise, I was going to go ahead and talk about our science. And then, Jamika, I don't know if you want to tell people how they can ask questions. I guess in the chat, people are welcome to ask questions, and we'll keep an eye on it and try to answer.
Absolutely, yes. So those of you joining us virtually, you are welcome to post your comments and questions in the chat at any time. And those of you here with me live, you can just come on over and we can take questions, or if you want to jot it down, you can do that, and then I will pass it along to the team.
Roy, so sorry, we're in the middle of a little bit of a busy moment, actually on Gemini. So maybe you can grab the, yeah, talk a little bit about the science.
Okay, will do. All right.
Thanks.
All right. So to put our science into context, this is an old slide deck I have, but I pulled it out of hibernation. So galaxies, like our own Milky Way, are not distributed randomly in the universe. They actually like to live together. But before we talk about how galaxies are distributed, I want to remind people that galaxies, like our Milky Way, are not just piles of stars. There's a lot of gas in some galaxies. There's dust, and in most galaxies, the majority of the mass is dark matter, which will be relevant to some of the things we'll talk about later. In fact, in some galaxies, the very vast majority of the mass is dark matter, and some others it's not. And all this is held together by gravity, with most of the gravity often coming from dark matter. And here's an artist's impression of the Milky Way galaxy, because we can't fly out of the galaxy that far away yet. And galaxies, as we look at them in the relatively nearby universe, come in many flavors or morphologies, shapes. And these were classified by Edwin Hubble, after whom the Hubble Space Telescope is named, and who also discovered the expansion of the universe and many other things. So there are galaxies that are ellipticals because they are elliptical in shape, and they are often redder because they don't have young hot stars in them which glow blue. And then you have spiral galaxies, some of which have bars across them and some which don't, and those spirals are often bluish looking because very young, very hot stars, which live for a very short period of time, are blue. And that tells us stars must be forming in those spiral galaxies, because those very hot, very massive stars only live for a few millions to tens of millions, maybe 100 million years, and then they die out. So in order for the galaxy to look blue, it must be making stars today. Whereas these elliptical galaxies are not making stars. They don't have those hot stars in them. And you're probably used to seeing pictures of these spiral galaxies all the time because they're pretty, and rarely ellipticals because they're boring. They're very interesting, but they're boring looking. They don't make for pretty pictures. So I talked about spirals and ellipticals. And then there's a whole other category of galaxies that aren't on Edwin Hubble's diagram, which is irregular galaxies, which as we look further and further back in the universe, we see a lot more of them. And they've either had a collision, a merger, or they haven't had time to form their nice shapes yet. So if we look at what galaxies are made out of, they're made mostly of dark matter. So even though in our observations, we're often looking at the stars or sometimes the gas, we look at this plot on the size scales of the universe, and we have what's called the mass to luminosity ratio, like how much matter there is compared to how much light a galaxy is emitting. They have anywhere from up to 10 times as much matter as we expect from the light. And when you get to the largest structures in the universe, that the vast majority of the material is this dark matter. And for a long time, we've known that these galaxies, like our own Milky Way, are not just sprinkled across the universe at random. People looked at photographic plates back in the day when that's what we used, giant glass plates that were a foot on a side, and visually inspected them with little magnifying glasses, counting galaxies and marking them off, very painful. And they realized that galaxies are not distributed randomly, but rather in large structures across the universe, which we can compare to how people are distributed in the United States. So there's a map of the United States and our interstates and the population density. As it gets darker purple, there's more people, and then there's these big empty voids. And the bottom, I have a map of a little slice of the universe, and you can see the same kind of structure of filaments and voids. And we call the areas that are sort of the average density the field, like the fields of corn in Iowa. And the most dense regions are clusters, which can contain hundreds to thousands of galaxies. And then there's smaller groups, which are like our suburbs, like Hilo, small towns. And then they're connected by filaments, which are like, if you drive along the roads, you'll see population along the roads. And If we make a map of the United States, and I'm not making judgments about red versus blue here, it's just for illustrative purposes, you can see that if you go to different regions of America, you'll see changes in voting patterns. Denser regions of the country tend to vote one way, and less dense regions of the country vote another way. Well, interestingly, galaxies do the same thing, except with the colors flipped. In the densest regions of the universe, most galaxies are red, at least locally, are red ellipticals. And as you go outside to the field, you get more and more spirals. And if we go and try to map the universe, we can look at our local universe. And we're here, this red dot is the Milky Way, and every other little white dot in this picture is a galaxy. And these white lines show how these galaxies are going to move over trillions of years. And they're like the flow lines on a geographic map. And this is just our portion of the little portion of the universe, 100 trillion light years across or something like that. And what we can see is that these galaxies, are all going to flow together over time. So the regions of the universe, dense regions, get ever denser and denser, like people moving from the suburbs into the cities. And if we make pictures of the galaxies that live in different places, then we can see that as we look in the field, you have all these beautiful blue spiral galaxies. You have some red galaxies, but some of them are dusty spirals. But if you go into the denser regions of the universe, these blue galaxies, at least nearby, aren't there, or there's very few of them, and you have much more of these big, massive elliptical galaxies. And the question our group has been trying to answer for the past 25 years is why? Why does this difference exist? It's like a sociologist or an anthropologist asking, why do people vote differently depending on population density? What are the underlying causes? And just like with people, there's actually a lot of correct answers and some answers and a lot of wrong answers, and there's probably a big mix of things that are going on. And we've been trying to disentangle this over time with our studies. Now, it's true that galaxies look different in dense and in denser regions of the universe than in sort of average regions, but it's also true that galaxies change with time. So if we start looking back in time, then we're here today when the universe is 14 billion years old, and there's well-formed big elliptical galaxies, there's well-formed big spiral galaxies. But as we go back in time, unsurprisingly, galaxies are smaller and less massive because they haven't built up as much. But the fraction of ellipticals starts to get lower and lower, and you get more and more like young, messy, irregular galaxies. And not only do the galaxies look different as we look back in time, they look different in different environments in different ways. So it's like looking at how the populations in cities change versus how the populations in suburbs versus the rural areas change over time. And from that, our group is trying to disentangle, figure out what are the effects that are happening to galaxies to make them change with time in different ways. Okay. I think I'll leave it at that for talking about the galaxies. And for our particular research, what we are doing is I'll stop the share and let people ask questions before I talk a little bit about what our team is doing.
Thank you, Roy. Do we have any questions here so far about what we've heard on types of galaxies and densities and or anything else? Yes.
How does the movement of the galaxy correlate with the expansion or slower expansion of the universe?
Excellent. So how does the movement of galaxies correlate with the expansion of the universe?
So that's an excellent question. So galaxies, if you want to imagine in this sort of simple picture we often use in our intro astronomy classes, the universe as a balloon. And if you painted the galaxies on that balloon and you blew up the balloon, then the galaxies should all just be getting further and further away from each other as the balloon expands. But in reality, what you have is that when there are a lot of galaxies close to each other, their gravity holds them together, just like the stars within a galaxy and the gas and dark matter holds the galaxy itself together. So the galaxies, I actually think I have a slide. I don't know if it's in my next slide deck. Let me see if I can look in there. What happens is that the universe is expanding, but where there's matter, the structure is actually growing and the matter is flowing into there. So at the largest scales, the galaxies are flowing apart, but still the galaxies near clusters like flow down these filaments and build up the matter in a cluster. So the overall movement of a galaxy as we observe it is a combination of the motion due to the expansion of the universe and then the galaxy's own individual motion influenced by the gravity of the stuff around it. I think of it as a combination of like being on a moving walkway and your total motion is the movement of the walkway, which would be like the expansion of the universe, and your own walking, which is determined in part by the crowds around you and stuff like that.
Perfect, Roy. Any other questions before we delve into the science the C3VO team is going to be doing this evening? Yes.
How they take pictures of like the Milky Way galaxy, like when we're in it.
That's a great question that I'll throw out there to everyone. So the question was, there's some curiosity behind how do we take pictures of the Milky Way when we are in it? And that is that we really don't. Roy, do you want to take that, or anyone else?
Yeah, I'll take that since Brian said he was busy. We don't actually have pictures of the Milky Way from the outside, right? So that picture I showed, I said it was an artist's impression. So the pictures we have of the Milky Way are all from the inside, which is where we see that stream of like bright light and the dust and stuff in the sky. These maps that we have of the Milky Way are made by determining the distances to stars and then putting them out in a 3D map and then envisioning what that would look like.
Great question. Thank you. Any more questions? And so I see some other people have joined us. So we're taking some questions for the team before we delve into their science and start looking at what they're seeing on the Subaru screens. Nope. Okay. Well, if you do, yes, another question. Yes. Great question about determining the age of a star. Yeah, so that's to anyone. Rob, Finn, Joel. How do we determine the age of a star? And let me change the view here. Someone else want to take that?
Finn, can you take this one?
Sorry, what was the question, guys? I think I might be able to help, but what was the question?
The question is, how do you determine the age of a star?
The age of a star. Okay. Yeah, that's a wonderful question. It's very, very difficult is the answer. So some stars by, let's say, astronomer standards, live a very, very short life. So something like 5 million or 10 million years, that's a short star life. Some like our sun live about 10 billion years, and then some live like 1 trillion years. And so there's a standard relationship that astronomers have figured out from a long time ago between the luminosity and the temperature of a star. And so if you so luminosity is the intrinsic brightness of the star, so you have to know how far away it is, but there's ways to get that measurement. So the intrinsic brightness and the temperature, which you can measure based off of the chemical composition in the atmosphere of the star. So that requires spectroscopy, so breaking the light into a rainbow and then looking for signatures of hydrogen or oxygen or carbon, all things that we see in our own sun. And so if you plot up this relationship, for most of a star's life, it will sit in something called the main sequence. So for about 80 to 90% of its life, it'll sit on this main sequence. And so you can kind of tell, oh, okay, so the star is in its adolescence, more or less, or it's kind of transitioning to old age. It starts to get kind of grumbly as it gets older. So it kind of moves up and down on this plot. And then all of a sudden it starts to go a little bit crazy. So usually after it stops burning, so fusing hydrogen to helium, the star goes into a little bit of spasms. And you can see these spasms in this diagram. It'll move up and down, change temperatures, change luminosities, because it's not in what's called hydrostatic equilibrium. So the balance between the gravity and the pressure coming from the fusion in the core is out of whack. And that's when you start to think, okay, a star might be trending towards the edge of its life. So that lasts, depending on the type of star, that process can last anywhere from a couple million years to even 500 million years. But for a star like our sun, that process will eventually end in it shedding its outer atmosphere and turning into a stellar remnant, in the sun's case, a white dwarf.
Thank you, Brian.
And so as Roy mentioned, like red galaxies and blue galaxies in his talk. So usually stars that are young are blue, and stars that are a little bit older are red, or less massive are red. And so the elliptical galaxies, being red, are usually comprised of older stars, and bluer galaxies, for example, our Milky Way, at least in terms of what we see, the luminosity is dominated by younger stars.
Perfect. Thank you so much for that explanation. I do have another question. Yes.
Yeah, what are you looking for to like determine if there's life in space or potential for life? And have you found anything that's close to pinpointing it?
Yes. Okay, so the question is, what signatures are we looking for to determine whether there is life in the universe? And life, of course, is, there's some caveats to that. So maybe carbon-based life forms, but what signatures are we looking for when we look for life, and has that been found yet? I'm going to go out on a limb and say not yet, because I think we have heard about it.
Yeah. So I'll bring it back to our observations tonight. So actually, Gemini Observatory, the place that I work, is really good at this. So we have an instrument called MOIRCS, which is a high precision radial velocity spectrograph. And what that means is we can measure like really tiny pieces of the rainbow. So we disperse the light from a star nearby, and we measure really fine gradations in color. And why that's important for this particular question is that sometimes you have a star. I guess you guys can see my video. So star, planet, and Gemini Observatory on Maunakea. And so you have the planet that moves in front of the star. It actually occults the star, and you can measure the change in the spectrum of the star. And that change is due to the atmosphere of the planet, the exoplanet that passes in front of it. So you can actually measure the chemical composition of the atmosphere of these planets. And so MOIRCS has, well, we observe every night a large number of stars. There's programs that are looking for habitable planets in our local neighborhood. So without probably 100 light years, so not that local, not close by, but close by on cosmological standards. So about 100 light years away, and looking for basically any signs of life. And we've definitely seen oxygen in atmospheres. This kind of stuff that we're used to, oxygen, nitrogen. But as Jamika alluded to, we look for the things that we know. We know what the Earth looks like. We know what the chemical composition of the Earth's atmosphere is. We know that we're carbon-based life forms. And so, that's a helpful place to start, but that's not probably what all life in the universe looks like. And so we have to be very careful to not bring on our human biases and try to see, okay, might there be silicate-based life forms? And so what would the signatures of those atmospheres look like? But I do want to say that the observations that we're taking on Subaru tonight are not of exoplanets. So that what I just talked about, those star planet systems need to be relatively close by. We're looking Oh gosh, let me see if I can do the math. Oh, anyways, we're looking at billions of times deeper in the universe. And so we're looking basically at galaxies that look like points to us. And so we're just getting the aggregate emission from all the stars, everything that exists in those galaxies. So that's the observation on Subaru tonight. And Subaru is really great at that particular type of observation. And so we're not going to find any. It's very unlikely that we find any life tonight, let's say.
It would be exciting if the most unlikely thing to happen actually does happen. It would be
It happens a lot in
fantastic to be-
astronomy. Yeah, it happens a lot.
It does.
Serendipity is a huge part of astronomy. So
Yes, yes, Brian. Thank you so much. All right, great questions. Any other questions before we get into the science? Just come on over here and answer your question.
yeah, feel free.
How do we like know so much about the life cycles of stars if it occurs over like such a long period of time that like outlasts human like existence?
Yeah, it's a little bit like humbling. Like when we say like the term instantaneous in astrophysics means 10 million years. I mean, it's ridiculous. And so yeah, we get snapshots of luckily the universe is huge, it's varied, and we have tons of stars, tons of galaxies to explore. And so like our observations tonight are to collect a huge number of galaxies and then make a statistical analysis of those galaxies. And so any one galaxy is not going to, or any one star is not going to tell you the full picture, but you can start to pull together. You say like, okay, that star is blue, that star is green, that star is yellow, that star is red, that star is orange. This is the chemical composition that we see in their photosphere, in their atmosphere. Okay, that one's kind of like going a bit crazy. It's like puffing up, and what's happening with that atmosphere. And so you get all these snapshots together, and you start to piece together a film of that. And there's mistakes that you can make during that process. You can make false equivalencies. You can say, oh, this is like this, and that happens all the time in science. But luckily, we're always observing. We're always looking for new angles of things. We're always getting wonderful new instruments, new telescopes. The James Webb Space Telescope is up in the Lagrange 2 point in space. That's getting a different perspective at things, and so we're constantly challenging our pictures by new data and new simulations. And so I'm just talking about the observational side, of course, because that's where I work. But there's a bunch of really, I'm kind of a fake astrophysicist because I just use the telescopes to say, oh, I see that, I see that, I see that, I see that. Let me put together a picture. But there are like really smart people that actually calculate, sit down at a desk and say like, okay, a star should, do this and this and this, and here's how hydrodynamical equilibrium breaks. And, if this happens, then the star's atmosphere puffs up, and they say, okay, observers, is that true? And we say, yeah, actually, that kind of makes sense. Or no, that's not really what happens. And so then they go back to their desk and they write new equations and so on and so forth. And that's the wonderful life cycle of ideas in science. And so we're, it's constant positive feedback loop, I would say, that we're challenged to, do better, both from the observational side and from the theoretical side.
Thank you, Brian. Any other questions? Yeah.
It's like the holy grail question right now.
Okay, so one more question, and we'll delve into your science there. So the holy grail question, what's the quest right now in astronomy? And I know that's going to vary for different people, but Brian, Roy, Joel, Finn,
Finn, you want to take some? So Finn is just advanced to candidacy, so he's a PhD candidate. He has his whole life in front of him. So just 2 days ago, Finn, you advanced to candidacy, took a big test and stood up in front of everybody and told them what you were planning on doing. So you got your whole scientific life ahead of you. What's really intriguing you?
Well, yeah. So yeah, it was 2 days ago. Thank you for bringing that up, Brian. Oh, yeah. So I would say, I think there's a lot of different big questions in astronomy today. But I guess the questions that I try to study are certainly a subset of those questions. I think there are a lot of different avenues people go down. I would say that, people are concerned with cosmology, where the universe came from, how the universe is expanding, what that expansion rate is. People really care about, I know someone asked a minute ago about finding signatures of life. People study exoplanets looking for life a lot. I think that's one of the big questions. But I guess the questions I find myself concerned with more have to do with some of the science cases Roy was talking about a minute ago, in terms of looking at, the large scale structures of our universe, understanding how dark matter begins to cluster and come together, and when that happens, how do the galaxies in relation to these larger structures change and grow and evolve? How do they, become more star forming, less star forming? Why do they change their shapes? And all sorts of those kind of questions, to give a very, very broad overview.
Thank you, Finn. Wonderful. And congratulations.
Thank you.
That's absolutely amazing. So proud of you. Yes, you're getting lots of applause here.
Appreciate it.
Yes, yes. Okay, so thank you all for the amazing questions, and those of you in the chat virtually, of course, you can post your questions anytime. Okay, so Brian, Roy, Finn, Joel, the viz closes at 9, so I'm going to transfer host to Brian about 8:40, if that's okay, because then we got to pack up and drive down the mountain. But of course, you'll be able to continue the session until the scheduled end time at 9:30. Is that?
Oh, cool. Cool. Let's get into it then, because we only got about, what, 20 minutes for people there. So
Exactly.
Joel, do you think you could
Let's get to
share Gen2 _S7 screen, please?
Yeah, I can share that. Hold on.
So actually, for
Yep.
people that are there at the viz, we've actually been observing this whole time. So this is why we have 4 people on our observing team, because there's a lot of different things that are happening, and so we've actually been integrating this whole entire time, taking data, looking and basically searching for galaxies at the edge of the universe, and so this is our beautiful picture that Joel's sharing of what we're seeing on Subaru. And Roy shared some very pretty pictures earlier. This is not what this is, but this allows us to do our science. And so science isn't always pretty, especially when you're looking at the edge of the universe. Things all look like dots for the most part. And so we're observing, I guess a lot of people probably were up. Is it clear up there, actually, Jamaica?
That's a great question. Crystal, how does it look outside right now? Is it clear? It is. I see the moon.
See the moon. Okay, so that's the important part.
Beautifully cleared down here.
Wonderful.
Right.
Okay. Yeah. So I mean, if you guys have you can see the moon's super bright tonight, and so if you'd come up to the viz, a couple weeks ago, it would be super dark. You would be able to see the Milky Way, no problem. Now we're almost to full moon. I think we're at 92% illumination tonight. And so it obscures a lot of things, even with your eyes. It's a very different sky that you see when the moon is out. And so one way that we get around the moon is by observing in the near infrared. So these are wavelengths that are redder than red, than we see as red. And the sky isn't actually as affected by the moon in the near infrared wavelengths. But the sky is also very bright in the near infrared wavelengths. And so we have to take a picture at one portion of the sky, and then we have to move the telescope a little bit and take another picture, and we have to subtract those two because the background is so bright as compared to the objects that we're looking at, that we need to remove that background. And so that's what you're seeing here. You're seeing dark spots and you're seeing light spots. The light spots are the galaxies and stars that we're seeing in the image right now. The dark spots are those same stars and galaxies that we saw in the previous image. And so this is a very typical pattern that you see in near-infrared imaging observations of one bright source, one dark source, and then we combine all. So this is just two images that we've taken. Each are 2.5 minutes exposure. And so this is 5 minutes total of exposure that we subtract. And then we have been observing the same target, so the same patch of the sky now for almost 2 hours. We're going to keep going. I was hoping that we'd be able to switch fields while y'all were watching, but we're not going to finish this for another 30 minutes, I think. So in total, we're going to be observing this part of the field for this part of the universe for about 2.5 hours. So it's a huge number of these exposures, taken one after another, after another, after another, just moving slightly around in the sky. We're going to combine all that, and we're going to get a really, really deep image of the sky. And I think actually, so there's a couple of really important people that you guys are not seeing on your screen. And they are, let's see. I don't know, they're here in this computer here. So they are the super support astronomer and observing assistant up on the summit. And they are helping us with all of their wonderful technical knowledge and their ability to move the telescope with our observations. And our support astronomer, Ichi, is now combining all of our images. And hopefully within the next, it takes a little while because we have a lot of images, but hopefully in the next 5 minutes, we'll be able to show a picture of all of these images combined.
Fantastic. We're definitely grateful for all of the support astronomers, your work that you're doing to enable this kind of research and to allow us to be able to see it as we shadow the C3VO team. Now on screen here, thank you so much, Joel, for sharing your view with us to allow us to have a bit more immersive experience. Things are changing, and now we just have a plot that just appeared on the left, and got some things that are being circled. What are we seeing here, Joel?
I believe Brian is going through the main image that was taken, and he's trying to find out which sources work best. I don't know exactly what he's doing on IRAF in the top left. Looks like some sort of contour map, if I'm not mistaken.
Yeah, Joel. So what I'm doing right now is assessing the quality of the data. So we have a lot of factors that go into like how long we want to look at a particular field on the sky. We're looking really, really distant. So automatically that means even with this huge telescope and this really wonderfully sensitive instrument, we have to observe for a pretty long time. But clouds, of course, matter because if clouds come in, like last night, we had a really amazing looking lenticular cloud that was basically sitting right over Sub-Millimeter Valley and just to the west of Subaru. And our first target, the first place that we wanted to look in the sky was smack behind that lenticular cloud. And so we measured something at Gemini, we measured something like 5 magnitudes of extinction for that cloud, which means that for every one photon that comes, for every one photon that comes in from the universe, 100 were emitted by the source. So that's not a very efficient place to look. And so very luckily tonight, actually, so yeah, can you go? Maybe people in the Viz can see this already, but Joel, can you go to Gen2_S8?
1 second. Let me just go to I think I've loaded up. Sorry, I have to like a little taskbar. Okay.
Thank you, Joel.
1 sec. Of course. Next on here. Let me just reshare real quick. S8. There you go. Perfect.
Yeah, thanks, Joel. So that's what it looks
Course.
like up on Maunakea. That's the Subaru all-sky cam there on the top left. There's a YouTube streaming service by Subaru, which is wildly popular, which is kind of always streaming effectively. You can see all sorts of really neat things randomly above Maunakea. Meteor showers especially are awesome from there, as are bolides. And then on the bottom right or the right side, you can see all the Gemini cams that are facing different directions. So we actually have we're looking pretty close to the moon tonight. And we have a pretty clear sky up there. So actually the clouds aren't making too much of a difference, but another thing that we have to be really careful about is the turbulence on the ground and the turbulence in the atmosphere, which can cause sources to be blurred out. And if they're blurred out too much, we aren't able to see them very well. It's like squinting your eyes, or all the photons get dispersed out, and then you're not able to see what you want to see. And it means you have to take deeper and deeper pictures when the blurring is more and more. So I was just assessing, if you can go back to the other screen, Joel, the S7. Yeah, so I was just assessing. So I just subtracted off the last two observations that we took. And this is a radial plot of a point source, or probably a star or a very distant galaxy in the image. And it gives me these numbers. So these numbers are how wide or how blurry basically this object is in terms of pixels on the detector. And so I can convert that to an angular size on the sky, and I can say, that's really sharp, like it looks really sharp tonight, or no, that actually looks like super blurry and we need to look for longer. Another thing that we check, and Ichi is our support astronomer is amazing at doing this, is looking at how round the stars or point sources look, and it doesn't look great in that. Let's see, like something like that. So that this is a contour plot, and so it gets brighter and brighter towards the center, and you can see these are pretty circular, these contours here. And so if these start to get a little bit fuzzy, so if we see astigmatism, for example, so where it gets elongated in one direction, then we may focus the telescope, and so we'll refocus, and the focus can change based on the turbulence, it can change based on temperature, so on and so forth. And so every once in a while, we get images that are not quite as sharp as we would expect, and so we do a focus run. And so this is something that we just keep an eye on every time we take an observation, or maybe every third or fourth observation. We just want to double check, are we seeing things that we expect, or like in terms of the bright sources, or do we need to do something, or do we need to integrate for longer? It actually looks like, yeah, we're in focus, and the turbulence is not so bad. So we actually have a pretty beautiful night, and it was predicted not to be great. So right now, we're very, very happy.
I'm happy for you, because I definitely was looking at the weather forecast for the afternoon, and I was a little anxious about it. So I'm so excited that things are clear and going well. Okay, so we have 8 minutes left before I will need to transfer a host over to you all.
Joel, actually, could you share Gen2_S1?
S1, yes, I can. Just find it real quick. Should be under this tab right here. I can shift this down here. There we
go. Great, thanks. So yeah, this is so Ichi just did this reduction for us, and it looks like there's 39 total images that went into this. This is a very quick reduction, so you can see artifacts in the image, like these streaks here. This will likely go away when we do a more careful reduction. And And you can see like here, there's kind of a ring around this source, which is a local background subtraction issue. But this is, almost 2 hours of observations all combined together. And these are the two channels, the two detectors of the instrument that we're using, MOIRCS. And so what we'll do later tonight is we will compare this image with another image. So what we were observing in what's called a narrowband filter, which is just collecting a little tiny bit of light over a certain color range. So we're looking in the near infrared, and we're just collecting very specific photons that should correspond to emission from doubly ionized oxygen in the galaxies in this structure that we're trying to understand better. And so what we do is compare that to another image that collects a lot more light over a broad wavelength range. And we look for galaxies or objects that are really bright in this image, but not so bright in the other image. And that's what we call a color in astronomy. And so if we can see, we'll basically blink these two images together. And if we can see objects that kind of pop out in this image, so just kind of like flashing beacons, we can tell, well, with a fairly high degree of certainty that those galaxies are sitting at this distance in this particular structure. And so then the basic science question is, let's count them up, and let's measure their brightness, count them up. How many do we see there? And is that within expectations of what we think is supposed to be there? For example, how much mass is supposed to be there? How many stars those galaxies would be forming if they were kind of typical? And if we see changes, then we can say, aha, maybe there's something funny going on in this system that's changing the number of galaxies. So maybe Finn's research is on merging of galaxies. So maybe they're all close together and they're merging and they're going crazy. Or maybe there's some process that's fueling more gas into these galaxies and it's causing them to form a bunch more stars. And so we have no idea. And these observations will help us understand that. And I just want to say, like, the faintest things in this this picture are 10, 11, 12 billion light years away. So no joke, very distant.
That's extremely distant. And so the instrument that you're using, MOIRCS, does it specialize in being able to see these very distant, faint objects?
Yeah, so what's wonderful about MOIRCS is it has this incredible, well, it's behind 8.2 meters of glass. So that's really, really important, as Roy mentioned earlier. It has 2 infrared detectors, so it has a relatively wide field of view for the infrared. And it has this wonderful complement of these medium band and narrow band filters, but you can match up. This filter actually was made for a transition of hydrogen in the local universe. So it was actually intended for imaging local galaxies, but it just so happens that it matches up with an emission of oxygen at the distances of this particular structure. So we've used it in kind of an innovative way to look at galaxies that this wasn't necessarily intended for. And so with all these different filters, we can actually match up for structures that are at different distances and for emission of different elements. Like, oh, yes, we'd like to look at this one with this particular filter, another one with this filter. And it's wonderful in imaging because you don't have to select the galaxies. You just look at that part of the sky and you get everything there, as opposed to spectroscopy, which is the other main method for getting distances to galaxies, where you actually have to put a slit most of the time on the source. You have to say, yeah, that's the galaxy I'm interested in, and those are the 4 galaxies that I'm interested in. Here we have no precondition, we're just observing.
Amazing. Thank you. Thank you. And so I was just told that we can go a little bit longer to almost the top of the hour, so maybe about 12 more minutes, which I'm super excited about. And so as we continue looking at the science that you're doing, perhaps someone could share with our audience how you come up with your observing plan. What are you going to look at, and how you decide which instrument at which observatory would best suit your needs for your observing goals.
Roy, are you online? May you feel that?
I just hopped back on, but I didn't hear the question.
So basically how you choose the observing plan, and like, yeah, how did we come up with this idea? Why did we choose Subaru out of all the telescopes in the world? How do we get time on Subaru?
Oh, there's a lot of moving pieces there. So I'll answer the last part first. So how we get observing time is competitive. So you have to write, typically with ground-based observatories, it's once every 6 months. With space-based observatories, it's about once a year. There's what's called the call for proposals, where scientists write proposals. We say what we would like to observe, what is the science we want to do, which camera on the telescope we want to use, for how long. And then a committee looks at those and ranks them, and the best ones that, according to the committee, get time. And depending on the telescope and what university you're at or institution and what access they have to various telescopes, between a half of proposals to an eighth of proposals, like or a tenth for like Hubble and James Webb, actually get time. So we're often told no. At University of Hawaii, you have access to all of the observatories on Maunakea, so we get told yes a lot more, which is one of the benefits of being here as an astronomer. So we've been studying galaxies and their evolution over a long period of time, and we're always trying to think of how can we find these galaxies, how can we differentiate them in an efficient way. So one way you can find galaxies at this distance is to take the light from the galaxy and break it up into its entire rainbow of colors called a spectrum, and then see like the actual emission line from this doubly ionized oxygen and other things. But when you do that, you need to take much longer exposures because you're spreading the light up. It's like taking paint and spreading it out over more and more wall. So this idea of using filters at very specific wavelengths, these narrow band searches for galaxies, has been used in a lot of different astronomical contexts. So we're borrowing ideas that other astronomers have come up with, and then we basically say, oh, well, we could find galaxies at these redshifts if we had the right filter. Let's go find a telescope and camera that might happen to have the right filter that we have access to. And lo and behold, Subaru had one of these filters. That's the sort of simplified version of it. But in a more general sense, when you have a scientific question or an astronomical question for which you want to take an observation, you ask, okay, what's the physical thing that I'm interested in? How can I go about detecting it or finding those kinds of objects or whatever? And you have to have a bunch of creative ideas about that. And then you have to figure out what tools you need to do that. And either you have to go find the tool that someone else has made, which is what we've done in this case, or you have to build the tool. So Subaru was built, and this camera was built to answer a bunch of scientific questions. So astronomers get together and say, what are interesting scientific questions, and what are the tools we need to answer them? And then they make them. It's not like building a house and saying, I need a hammer and some lumber, and I'm going to go to Home Depot and get it. In many cases, the tools that we want to use don't exist, and we have to develop them. So a lot of the development of these tools comes from other astronomers who have scientific questions, and they're like, oh, the tool to answer that or make that observation doesn't exist. And we're benefiting from the work that they have done and using their tools. Sometimes in innovative ways, just like you might use a hammer to do something someone who created the hammer didn't intend it for.
Yes, yes, absolutely, Roy. Thank you. Thank you so much for that. We during that explanation, we also had some questions about the percentage of staff in general at an observatory that is astronomers versus technicians, engineers, and all the other roles that enable this kind of science to happen. So maybe could one of you speak to that?
Yeah, I'm
And
happy to take
then-
that question.
Thank
Yeah,
you, Brian.
Yeah, I'm happy to take it. So actually, honestly, I don't know the exact distribution, but it depends on what you call an astronomer, first of all. I mean, everybody at the observatory is working to make astronomical observations possible and get the the most leverage out of every second that we have the privilege of being on Maunakea, to get the best science possible, because it deserves it. And so in one sense, everybody's an astronomer that works for the observatory, whether it's people that are doing outreach with the community, it's people that are building instruments, it's people that are testing the software, it's people that are facilitating staff in terms of human needs. But like for PhD astronomers, it's actually not that many. So I would say about 10% of the staff.
Yeah, we usually started Judd and Brian, like when we do career days, yeah, we say 10 to 20%. And just to
Yeah.
add to that, like I'm at the Institute for Astronomy, we're part of the University of Hawaii. So we run some of the observatories, but we do teaching, outreach, all kinds of stuff. And even for us, it's like 30% of our staff are PhD astronomers. The rest are graduate students, administrative staff, engineers, computer people, HR, all that kind of thing. So astronomy is made possible by something like 80% non-astronomers. There's only something like 10,000 PhD astronomers on the planet. And that all the other people who make it possible, whether the people who make the computer networks work or get the visas for our international astronomers or, get our paychecks, they're what enables all of this to happen.
Yeah, and I know for a fact tonight, the person who's operating the Gemini North Telescope, she is 24 years old. She has an undergraduate degree in mechanical engineering, and she is amazing at her job. She's one of our best operators, and she has effectively no experience in like formal training in astrophysics. A lot of what's learned, and including for myself, is all on the job training. I mean, I came in with an academic background, and then you come in and there's this huge machine with a ton of electronics and all this other stuff. I had to learn a ton about that. And luckily I came into an observatory environment where there was, first of all, amazing people that were willing to teach me, but that had just incredible knowledge about these subcomponents of the telescope. So it's all interlinked. If we can have the best scientific ideas, blah 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 blah, if we don't have the best site in the world, if we don't have the best telescopes in the world, then we can't actually test our ideas. So yeah, it's all interrelated.
Even things as simple as even if the road isn't graded and you can't drive up to fix the telescope, right? Or there's no internet connection, none of this works. So it really does it takes a village.
Brilliant. Thank you so much for that comprehensive response there. Absolutely, it does. And I see that it seems like some images have changed. Oh my goodness. Joel, Finn, Brian, Roy. Let's see. Oh, okay, no worries, Roy. Thank you so much. We'll look forward to seeing you in our next session. Thank you for everything tonight.
Thank you, Roy.
But yes,
Thank you so much for stopping by. So I just learned actually they're having a little bit of a problem on the Gemini telescope, so I might have to jump out as well. So maybe we could end the session after things finish up with the viz. But yeah, I did want to say that, so Ichi, our support astronomer, is manipulating the image here a little bit. He's doing smoothing on the image, so blurring it out just a little tiny bit, which helps reduce some of the noise in the image. And allows us to kind of bring out the background galaxy. So these little tiny points of light, for example, I don't want to mess with Ichi's cursor, but these little tiny points of light in this deep, vast background of the universe. So these little tiny points of light are really what we're interested in. And so this smoothing process helps a little bit to to bring out some of these sources that otherwise would be lost in the noise. And so in this image, actually, that he's inverted the colors, so the dark is actually light and the light is dark. And that actually helps I always do this when I search through images, because it's actually a lot easier for the human eye to be able to pick out dark on light than the reverse. So most of my undergraduate work was just staring at thousands of spectra, mostly noise. And I'd always invert because I was looking for these little tiny very dim galaxies in this vast data set of noise. So just, I guess, since you guys have to leave pretty soon, yeah, so we're coming close to, this is basically what we do all night. We take images in different parts of the sky. We're gonna move to another structure shortly, probably in, I don't know, 20 minutes or so. And we're gonna kind of weave our way around the universe, taking pictures. And if everything goes well on Maunakea, still very clear and not incredibly humid, although it's creeping up, yeah, we'll just be taking pictures all night.
Brilliant, brilliant. Thank you so much. Thank you so much, Brian. And maybe we can end, I'll let you get to your, I know you're doing support for Gemini, so thank you so much for splitting your time in a zillion directions to enable this shadow session, Brian. Maybe we can end, Joel, Finn, at least end on our end, and then maybe I'll make either Brian, Joel, or Finn the host, and because we can continue with one of our amazing participants, as always, Rob. Rob, always such a joy to have you. So the last question that we just got here, Joel and Finn, was about your path to becoming an astronomer. You know, what does it take? What classes are necessary, what skills are necessary, and I know that's going to vary depending on you know, who you are and just how you came to the field. But perhaps Finn, you could share a little bit, and then Joel, certainly would love to hear from you before I transfer host over to one of you. Thank you.
Yeah, I can talk about, I guess, my personal path a little bit to astronomy, but I could just talk about, you know, paths to astronomy in general as well. I think for myself, I've always really liked math and science and physics in particular, and I think those are, you know, if you enjoy at a very base level some of those topics, astronomy is already a potential landing spot for you if those are things that interest you. But I think it comes from a curiosity for a lot of people for the night sky, trying to understand our universe, our place within the universe, right? You know, there's you know, our world's a very big place, but you know, the universe is a little bit bigger, and there's a lot of things going on up there that we can look at, whether that's, you know, black holes or stars or other planets and things. And so I think having, you know, curiosities about those sorts of things, and enjoying some of the math sides of it, I think it all really comes together well. And so for myself, I always liked physics as a growing up, and then I learned astronomy was a thing. I tried it out at actually at University of Hawaii over like a summer when I was in undergrad and college, and I really liked doing research. I thought coding and playing with data, you know, understanding galaxies was a really cool thing. And so then I decided to apply to grad school. Things worked out, and here I am today. So can't complain.
I'm almost there. I already finished a couple of my applications for that. Are y'all able to hear me? Or
Oh yes, we
so
absolutely hear you, Joel.
okay,
Thank you.
I'm just making sure. So mine was similar to Finn's, like interest in astronomy. I loved the stars ever since I was little. I would just look up in space and I'd be like, I want to study that. I couldn't really conceptualize much. Of course, it was just kind of space, this like unknown that I want to learn more about. That curiosity just kind of stuck with me throughout my entire life through like a lot of like the childhood dreams, like some of them die up, but mine just kind of, I just always loved it. And it kind of evolved from astronomy into astrophysics. So I decided to apply to a few college programs, and I got in. And you have to, I mean, going through college, you have to learn just at least my college had this, you have to take a few astronomy courses. So one's learning about the stars, another's about the galaxies and how they work, how they function. I'm taking another one this upcoming semester about planetary astrophysics, just because I want to get like the best background possible. But I think that's the most fun, I mean, at least most fun that I've had just learning astronomy is through research, because that's, you get to actually, you get to learn, you get to study, and like these unsolved mysteries, you get to try and find out stuff that no one's ever seen before. And I think there's nothing else like it. But I'm in the process of applying to grad school right now. Hopefully I get in. Finn's already almost like done with, or Finn's already a PhD candidate, which is amazing. And he's got a few more years left.
Joel, we know you're going to get there, Joel. So we'll look forward to that announcement, hopefully in one of our upcoming C3VO sessions with you all in the future. Thank you so much for sharing that. Any other questions here from the audience before we wrap up on our end? No? Okay, so I'd like to certainly thank everyone at the Viz for hosting us. We are very thrilled to be able to have, oh yes, absolutely. Rob, we're always so appreciative of you and so thankful whenever you are here. Thank you so much, and you know that you are always welcome to post your questions, comments anytime. And as I am going to transfer host to someone, Joel, Finn, Brian.
Jamika, I think it might be best if we end the session here, unfortunately, because I'll have Finn, this will be the first night that Finn will be operating a little bit on his own. And I have to run over to Gemini to help them with something. So I think it would be good to call it here, but we'll have another session, public session in January, in the middle of January. And we also have a public session for Gemini later this month. So there'll be plenty of opportunities to observe what the Maunakea observe us observing on Maunakea. And we very much look forward to people joining us then. And thank you so much, Jamika, for going up to the Viz. And thank you everybody at the Viz for, I don't know, being interested, being up there, checking things out, checking out the stars with us. It's great.
Absolutely. Thank you all so much for allowing us to shadow you as you do your amazing research. We look forward to joining you again in the future.